So TDM Protocol is a digital audio communication meant to communicate many audio channels all at once in one stream. And a question came up in the forum just a couple days ago where it didn't appear to be working. So and the question was seeing this waveform, which certainly doesn't appear to be anything useful. So to investigate this, I decided to try it from scratch. So I went into the design tool, and here we scroll down, and TDM is near this list of outputs, and you just drag this onto the canvas, and then to give it some data, I decided to take just a sine wave synthesizer and connect the sine wave to the first of its many outputs. And if we look at the TDM documentation here, it's designed to transmit 16 channels and all these various bits. We'll take a look at that more in a few moments. So to use this, you, like anything else in the library, you export the code, and we'll just copy all this to the clipboard. Then we'll come over here into Arduino and paste it. There it is. Now to make this run, we have to create memory with audio memory, just some arbitrary number. And this is one of the things that was wrong with the code on the forum, is missing this audio memory. Then to make this work, if we come back into the design tool and we look at the sine wave, all of the audio library features have this documentation panel when you click on it, and we need these two functions, amplitude and frequency. So if we come back into Arduino, we'll just take the sine wave, copy it, paste it here, dot amplitude, and we'll give it an amplitude of 0.9, 90% of the waveform maximum. And if we copy it again, we had one more function that we need, which is frequency, for EQUENCY, and let's give it 220 hertz, just for testing. So this should create a working program. So we'll verify, and while that's working, we'll plug the Teensy in with this USB cable over here, and then from Arduino, we'll just upload the code. And now the Teensy should be running, and it should be transmitting the TDM data. So let's connect these oscilloscope probes. But before we do that, let's come back into the design tool one more time. And in the design tool, let's look at the TDM object here. And over in the documentation panel, here is where it tells us which pins it will transmit all that on. And we're not going to look at this M clock signal, but we are going to look at B clock and WS, the word sync or frame sync. So and those are on pins 20 and 21 on the TC4. So let's come back over to the hardware, and I've got a couple of oscilloscope probes here. I'm going to just, hopefully you'll be able to see this in the video. I'm going to just connect the ground to this ground pin here. And then I'm going to count the pins over. It says 23, 22, 21, 20. And likewise here for the blue signal, we're going to put that on the next pin over, which should be 21. And I'm going to connect that to the ground also. Let's turn this back over. So now we have the two oscilloscope probes connected, and look here on the oscilloscope, we have these two little yellow pulses. We have a delay offset here. So here are 3 little yellow pulses and a sea of blue. So let's just zoom in, and we can see that the blue is actually a repeating clock, and that the yellow pulse is, let's bring the blue right up here and just look at it. So during the rising edge of the clock is when the data is valid. And that's important. All of this is rising edge is when the data needs to be valid. It changes on the falling edge because it doesn't need to be valid. So let's have the oscilloscope measure these waveform frequencies. So turn on the waveform measuring menu, turn off this cursor, go back to the waveform. I want to add a frequency. If you scroll down here, I want to add a frequency counter on source 1, add the measurement. And there we can see it's 44.1 kilohertz. let's add, we can only add one counter. Let's add frequency, and let's measure that blue extremely fast waveform, and we'll add that measurement, and then we can get rid of this people we don't need. So here we can see we have about 11, zoom in, it's about 11.3 something, and hopefully 11.3 is it's 44.1 kilohertz times 256, because they're supposed to be, now we don't have enough resolution. Let's turn off this cursor. We don't have much clutter on the screen. Unfortunately, this oscilloscope, you can see, is not a super high resolution screen. But the idea is that we have 256 bits or clock times. Scroll back out, move this over here, and go to a finer. I'm going to adjust this so that we get these clock pulses right on the edges of the oscilloscope screen, so that we're looking at, there, I fine adjusted it. And this is, like with all use of oscilloscope, you spend a little time fiddling to get it set up. So here we're looking at one frame of 256 bits. Now let's come back over to the hardware, and I'll tip this up here. I don't know if this is going to be visible. Hopefully, amateur filmmaking techniques. I'm going to connect this. Oh, and I just lost the two probes on the other side. Okay, I'm going to go back to that pin there. Connect the blue one again. This is a little bit awkward, but this is the way these things tend to go. So the blue is now connected. They're all connected. And if we look at the oscilloscope picture, here it is. We can see green data has appeared, and I'm going to bring it to the center, and I'm going to zoom in on it, really zoom in a little faster. And those rapidly changing, as I scroll here, those rapidly changing time slots are the bits. And if I hit the single sweep button, so the oscilloscope will do one capture at a time when I hit this button, there, that is the data. Each time I press this is one audio sample of that 200 hertz sine wave. If I let it run at full speed again, obviously it's much faster than our eyes can see. But the idea is this yellow pulse at the top happens at the last bit of the previous frame. So when you receive this data, or the chips that will receive this, or if you use an FPGA and you develop your own, this yellow pulse means that you're on the last clock of the frame, and the next clock cycle will be the first clock of the next frame of data. And you can see that those 16 bits are that audio signal. So let's make this a little more interesting. Let's come back out to the design tool again. And if we come back over here and come back to the synthesis and put a couple more sine waves on this. Let's put 4 total, and let's connect one here, connect one there, and one near the end. So these will just be adding 4 more sine waves to the output, and then we'll export again. We'll copy all of this. We'll come over to Arduino and paste it, and then now we have 4 sine waves, but we have to take this sine wave initialization code and turn on the other waveforms. So here I've just copied and pasted it, and I'm just filling this in. And let's give these some other frequencies. Let's make this one 100 hertz. And while you wouldn't be able to hear it, the software can generate very slow frequencies. So just for fun, let's try some very slow numbers here that are subaudible, but they would be usable as low frequency oscillators if we wanted to control parameters of something else. And we're just going to send them here, and hopefully they'll be slow enough that we'll be able to see the bits change in real time when we view them on the oscilloscope. And look at that, I've made a mistake. I typed a 5 when I meant a 4. Okay, now let's try uploading this to the Teensy. And okay, it's finished uploading, and if we come back over, the hardware still connected, and look at the oscilloscope, there they are. And it looks like visually we have 4, it might be tempting to see this, and you can see those waveforms are changing slowly as we had hoped. And it looks like we have 4 things around one pulse, but remember that little pulse there means the beginning of a time slot. So whatever will receive this data, I'm going to zoom out just a little bit, whatever would receive this, I'm fiddling with the oscilloscope dials that you can't see, but you can see it moving on the screen. So there is showing just the 256 bits across the screen. This is what a receiving device or receiving chip would see. And you can see that those two very low frequency waveforms are changing very slowly. We can actually see the bits moving around as we go. So let's try zooming in to this one just to see what it looks like, just for fun. So there is the 0.03 hertz waveform. We can actually see the bits moving around as we look at this thing. So this is what TDM protocol looks like. If you were to use this in a project, you can send up to 16 audio channels, 16 bits apiece. You can also send large amounts of data to an FPGA or some sort of a project. And if we go back to the forum one last time, what ended up happening was the audio memory was missing, and this original code was using the SD card. And I think what went wrong was this SD card probably didn't have this file with the correct file name, or something must have been wrong with the card. And so ultimately, if we scroll down to the end, I posted this program on the forum and the screenshot of what it should look like, and it worked. He got up and running, and this really makes my day when things go well for people, and we can get someone started with an electronic project. And hopefully this video, if you're ever going to use TDM protocol and consider what it might look like, if you're troubleshooting it, what you can expect to see on the scope screen, hopefully this will give you an idea of what to expect, and maybe you can make use of it sometime.